Section 4.7, Optimization. Next to related rates, these are the application problems that we deal with most frequently in Calc 1. And basically what this means is we want to optimize a situation. We want to find the best, whether that's a maximum or a minimum, for a certain situation. So example 1, you will work on a research and design team for the National Beverage Corporation, distributor of LaCroix sparkling water. You are given the task of designing a new can of the naturally essence sparkling water that minimize production costs. So the current can is 12.1 centimeters tall and has a radius of 3.1 centimeters. Come up with the dimensions of two new cans that hold the same volume, one with a bigger radius and one with a smaller radius. If we were in class, I would be having pairs of people do this, so I'm going to kind of zip through some of this. To find the volume, remember there's the equation of the volume of a cylinder. So if I use that and calculate this out, I find that the volume of my can has 365.308 cubic centimeters. I want you to go ahead and see if you can figure out if our new can was 4 or our new can was 2, so one smaller or one bigger. Or if you want, pick your own numbers and go ahead and figure that out. Since my volume is a constant, 365.308, I'm going to round that to 365. So if I plug in 365 for my volume and solve that for h, if I'm given my radius or I pick my radius, I can determine what my height is. So if my radius is 4 centimeters, my height is going to be 7.268 centimeters. And if I again use the volume formula, I find that my volume is 365.329. So still super close to what my original volume would be. If my can has a radius of 2 centimeters, my height is going to be 29.070, and my volume is also going to be 365.304. Now we have to determine the cost. So the aluminum for the side of the can is 0.00016 per square centimeters, but the thicker sheets needed for the top and the bottom are 0.0005 per square centimeter. Calculate the surface area of the three cans and then figure out the cost of producing each can. So again, I'd like you to pause the video. It gives you the surface area. So the surface area of the bases is the 2 pi r squared, will be both bases together. And then the surface area of the side, if we unroll that can, it's just a big rectangle that has the dimensions of 2 pi r and h. So go ahead and figure out the surface area of each of those cans. There we have all those calculated dimensions. Now if we were going to figure out the total cost, each of those in the top row is the surface area of the base, so we would have to multiply those by the cost of 0.0005. And the surface area of the sides has thinner, we'd have to multiply each of those by 0.00016. When we do that, we find that this is going to cost a little more than 6 cents an ounce. This one is going to cost almost 8 cents an ounce, or centimeter, sorry, square centimeter. And this is going to cost a little over 7 cents per square centimeter. Again, if we were in class, I would do exactly what this says, and I would have everybody go up and plot their cost with respect to the radius, so cost with respect to the radius on this graph. So I'm going to go ahead and plot some of these, and then you can pause the video and copy down where my dots are. So from this graph, we can see that if the radius is too small, it gets super expensive, and if we make our radius starting to get too big, then the cost increases as well. So that curve we just drew is relating the radius to the cost. Can we possibly find an equation for that curve? So given the radius and the height of a potential design, how could you write an equation for the production cost? Basically what we did was we had the area of the top and the bottom, 2 pi r squared h times that cost, and then the area of the can itself, unrolling that cylinder into a rectangle, so that area times the cost of 0.00016. Stepping away from 4a for a second, can we use the volume of the original can to rewrite the height in terms of the radius? And we already did that previously on the other page. The volume of the can is pi r squared h, but we know that the volume is constant, and then if we're just solving this for h, dividing both sides, we get h equals 365 divided by pi r squared. Now, can we write an equation for the cost with respect to r that gives the cost of producing the can only in terms of the radius? So basically what we're going to do is we're going to use this that we have for the h, and we're going to plug it up into that equation in 4a, and then we're going to simplify that so that we'll have the cost in terms of nothing but the radius. So I've substituted that value or that expression from part B into my equation in part A, and now we're just going to simplify that, clean it up and make it look a little bit easier to deal with. Now, how can we use this equation to find the least expensive can? For which radius is the cost of producing a can at a minimum? Hey, it's asking for a minimum. We can find this using our first derivative test. So use that equation that we have in 4c and find the first derivative. The first step of finding my derivative, 2 pi r squared is going to give me 4 pi r, still times that constant. And then the 730 over r, remember that that's the same as 730 times r to the negative 1. So negative 1 times 730 r to the negative 2. Now let's clean that up a little bit. Then we need to set that equal to 0 and find what our r equals. So again, pause the video and do that, please. Bringing the other term over to the other side, I get that they're equal to each other. Then I can multiply both sides by the r squared to get out of the denominator. And then dividing and taking the cube root, I get that the radius is 2.649. Now we're going to do the first derivative test. Doing the first derivative test, I find that it decreases and then increases, which means we are going to have a minimum cost if my radius is 2.649. So what is the height of this least expensive can? Well, we can go back up and use that expression that we have in section 4b above. And when I plug that in and then pop that into my handy dandy calculator, I get that my height should be 16.55 centimeters. And so now we need to figure out what is the absolute lowest price for which we can produce a can of LaCroix. This basically means that I need to find the cost of 2.649. So if I plug that into my equation at the very top of the page, actually it would be into 4c, because I could use the top one because I do have a height. Otherwise, if I want to use the equation in 4c, I can use that one. So I use the equation in 4c, plugging everything in, putting this into my handy dandy calculator, I get 0.066. So we can produce a can for about a little under 7 cents per can. As I said before, optimization is about finding a maximum or a minimum in some applied contexts. So what are the steps to go about doing this? The first thing, we need to write an equation for the quantity to be maximized or minimized. This could be an equation for a volume, an area, cost, distance, whatever equation that has you wanting to maximize or minimize something. Secondly, you're going to use any constraints that it gives you to find a relationship between a variables. This is going to allow us to rewrite our equation to be optimized with only one variable. So that secondary equation is going to allow us to write one variable in terms of the other variable, and then plug that into our original equation that needs to be maximized or minimized. And then finally, once you have an equation in one variable, you're going to be taking the derivative of that so that you can find the critical values to help you locate the extrema using the first or second derivative tests. All right, let's try some of these. Example number 1. You have 200 feet of fencing to enclose a rectangular field by your house. One side of the field borders a pond and does not require fencing. What is the largest area of the field you can enclose? First thing you want to do, in my opinion, is always draw a picture. It helps you see what you've got. It's telling me a rectangular enclosure, so I'm going to draw a rectangle. One side of it is a pond, so I don't need fencing over there. And I need to maximize my area. So the equation for the area is length times width, or x times y. And just so we're all on the same page, I'm going to label this side my x and this side my y. So now, what is a secondary equation I have? Well, I know that I have 200 feet of fencing, and that would be my perimeter, so that would be a secondary equation. My 200 feet of fencing needs to form my fence, so it's going to have to cover y plus x plus y, or x plus 2y. Now we want to write our equation that we're trying to maximize in one variable, so it's rather arbitrary. You could solve that secondary equation for either x or y. I guess I'm a creature of habit because I solved it for y, because it just always seems what you always solve equations for. So now I'm going to take that secondary equation and I'm going to plug it into my equation that I want to maximize, so I have an equation with just one variable. So now I've gotten my equation in one variable. I need to find the derivative. In this form, however, I'm going to have to use the product rule, and I'm not a big fan of using more rules than I need to, so I'm just going to simplify this by distributing my x in. And now when I find my derivative and with respect to x, I get 100 minus x. Setting this equal to 0, I can very easily find that my critical value is 100. So now I need to determine, does that in fact give me a maximum area? Using my first derivative test, if I plug in my first derivative in a number that's less than 100, I'm going to get a positive value. If I plug in a number that's bigger than 100, I'm going to get a negative value. So it does in fact increase and then decrease. So I'm going to have a maximum area when x is 100. And I can plug that into my secondary equation and find out how long my y should be. In this case, I can kind of use some common sense, and I know that my y is going to be 50. If this is 100, I only have 100 left for each of those sides, so it's 50. So I have a maximum area if my area is 100 feet by 50 feet. Making sure I answer the question, it asked what is the area of the largest field. The area would be 500 square feet. Example number 2. A rectangle has 2 vertices on the x-axis and 2 vertices on the curve of 9 minus x squared. What is the maximum area of this rectangle? Well, as the hint says, let's sketch a picture of that. So here's my picture, and we want to maximize the area of the rectangle. So the area of a rectangle is length times width. If I look at my rectangle, I don't necessarily need a secondary equation this time. If I look at my rectangle, my length is actually, from here to here, is actually a length of 2x. And then my width from here to here, in order to find, so I'm going from 0 up to this point, so my height is actually going to be that 9 minus x squared. And that's going to be my area of this rectangle that's bordered by that semicircle. Simplifying that so I don't have to use the product rule, I can just differentiate it. I'm going to get 18x minus 2x cubed. Now we need to find the first derivative and set that equal to 0. There's the first derivative, setting it equal to 0. Setting that equal to 0, I get that x equals the square root of 3. So now I need to do my first derivative test. The square root of 3 does in fact give me a maximum, so to find out what my area would be, I'm just going to plug that back up into either one of these, my original formula for the area of this rectangle. Plugging that back up into my area, I get that my area, maximum area, would be 12 times the square root of 3 units squared. And the last problem, a sheet of cardboard with side lengths of 60 inches is folded into a rectangular box with a lid. 4 squares with a side length x and 2 rectangular regions are discarded in order to fold the box as shown. So I'm going to go ahead and label all the parts of my box because it's going to be a length, width, and height deal. I need to know where's my length, where's my width, where's my height. So when I look at this problem, my length, if this is my length, it's going to be 60 inches minus those 2 x's. And now to find my width, this is a sheet of square sheet, 60 inches, so if I were to cut that in half, my width is going to have to be, this is 30 minus that 1x. And then my height, it's going to just be folded up as x. Please pause the video and multiply all that together. I get this by multiplying it together. So now in order to find a maximum, I need to find the derivative and find my critical points. So this is my first derivative, so now I need to factor it and find my critical points. And I get my critical points are x equals 30 and x equals 10. So now let's do the first derivative test. Here's my first derivative test, so since it increases and then decreases and then increases, it's going to have a maximum volume when x equals 10. So the height of my box is going to be 10 inches. And just to finish it up, the total volume of my box would be 40 by 20 by 10 for a maximum volume. Please come to class if you have any questions. These can be tough questions to do.